Hey, so hello, welcome everybody. As you probably know, I'm Jeremy. I'm just gonna go ahead and introduce myself because that's probably what I should be doing at the beginning. So, I'm Jeremy. I'm in 11th grade, and I took the AP Physics 1 2 years ago. So now I am here trying to give that back to everybody else. And what was I gonna say? I forget. Well, this is gonna be an interactive session. So I have written 3 problems. I hope they're fun and hopefully they're nothing like what you've seen before, so you can get some kind of new intuition. And the idea is that you guys will be solving them with me, or more like I'll ask you questions and then you yell at me in the chat to tell me the answers. So awesome. Yes. Yeah, use the chat freely because I assume there's like way too many of you to actually turn on your mics or anything. But I would, I'm not against seeing your faces or anything like that. But I assume that none of you would be the first person to do that. So I'm going to go ahead and start. Oh, well, first I want to know a little bit about who's here. So those of you who have access to the chat, like, can you type in your grade so I can see what grade people are in? Oh man. Okay, 15. Did someone say 15? Did I read that right? That's not a grade. Wait, what? 10. All right. Yeah, 6. That's pretty insane. 12. I'm what? I'm so confused. Okay, take your time. Well, and yeah, 0th grade. Coming out of the womb to take physics AP. Can you also how about everyone write how many years they've studied physics? 1. Okay, that's what I would expect. 0. Okay. We love that. I assume you're rounding down. Otherwise it'd be a little okay. Or I guess like not officially studying in school. Maybe you're counting by a different metric. That's fine. Okay. So hopefully I'll go ahead and share my screen so you can see what I've done. Oh no. Wait. Oh shoot, I think I did it wrong. Hold on. Wait, how do I go back? Someone explain to me how to, okay, there you go. Wait. I may want to do something else. Let's really quickly undo that. Where's my mouse? There you go. Yes. Okay, this is what I want. So what I'm going to be trying to do here is I'll show you a problem like this or something. And then oh wait, how many people are in this? 113? Well, okay, we'll see how this works anyway. So I'm gonna, like, first, for example, one of the things I'm gonna do is ask you to draw a free body diagram. And then if you guys, I think I have annotation on. So if you would like to annotate where the arrow is, then we'll see what happens and hopefully they won't crash Zoom. I probably I guess considering the number of people here, I probably won't do that. Annotate is off. Okay, I'll turn it on. But I'm not super optimistic. We'll see. Okay. 113. Yeah, I agree. Oh, okay. I want to see what happens. I mean, not everyone has to do it. Like, well, okay. We'll see. We'll see. Wait, can I enable annotations? Isn't it in the options over here or something? Oh, okay. I guess it's off. Oh, that's like a fail. You can only enable before a meeting. Yeah, I agree. I think. Okay. Okay. It's cool. It's cool. We do not have annotation. Okay, so yeah, I'll just talk and then you guys can spam the chat because again, the idea is that you will be solving the problems, not me. Okay, so we'll be going, so here's the first problem. The problem deals with blocks on an inclined plane. I'm sure all of you have seen this before. This is like a stream. I haven't watched this stream before. No. Okay, so you can probably read, but I'll read it for you. A single block of mass m is placed on a frictionless inclined plane with angle theta and allowed to slide. So starting pretty from the bottom here, draw and label all the forces on the block. So throw out the names of the forces that you can think of that are important here. Oh, I said frictionless. Oh wait, bro, I turned off annotation. How am I supposed to? Wait, okay. I'll make do. Yeah, okay. So everyone tell me if you can see this. Hello. Yes. Okay. Yay. Then we have our inclined plane, we have our angle, and we have our mass. We have mg here, as all of you have said, and this is our normal force here, as expected. Okay, Discord. Oh my god. Okay, go back. Next. So now we have two frictionless blocks on the incline. One is on top of the other one. They have masses m1 and m2 as indicated. And now we want to draw the free body diagrams of both of these blocks. So I guess I'll just replicate the diagram because that's my only option here. So M1, M2, M1 is on the bottom. Okay, well, I didn't even, yeah, go ahead. So let's start with M1, or let's start with M2 actually, I lied. So what forces are important here? Again, they're frictionless right now. That's what I've said. I'm not drawing with a mouse. Yeah, like I wish I had skills. Okay, M2G. I'm pretty sure everyone knows what's going on here, so we'll just go ahead and, well, someone has written F1 too, so we'll go with that. Now, what about M1? What is going on here? No air resistance, ignore air resistance. We are living in physics world here. Still gravity, yes. Oh, that's not what I want. This boy. Sometimes. All right, keep spamming, guys. Pi equals 3. Okay, well, what I wrote is F12 here. Let's just call it F normal because, like, this is a normal force. You can also label it F12 because it's the normal force of, yeah, of block M1 on M2. Oh, yeah, actually, I'll go back to writing 1, 2 because it's 1 on 2. Or should I write 2, 1? I don't even know. So I've seen a couple of people say things about M1, but I want to see more because I've seen different answers, a little bit of a disagreement. Yeah. Okay, force from M2 to M1. Force on box 2 to box 1. I assume, you guys are just, okay, I assume you mean this. Normal force from plane, one from, yes, okay. How do I denote this? Plane on 1. Okay, it looks like you guys know what's going on. So yes, that is our final answer. We're good. We are good. Let's go back. So next part of the question. Now, suppose there is static and kinetic friction with coefficient mu between the two blocks. So, well, we've already drawn like the forces. I'm sure you can all agree that those forces that we drew already are still here, right? But what does the friction look like? Let's draw the forces there. Now we have friction. Where does the friction come into play? To be more specific, like on which, let's say like mass 2, where is the friction? The friction coefficient is mu. Mu. Oh, why is it doing that? I'm angry. Mu. Okay. Hmm. Hmm. Everywhere. I think that's not correct. Okay. So most people have been saying for M2, are you guys saying for M2, friction goes this way? Hmm. Okay. So, how do you know the friction goes this way? How do you know the direction of the friction at all? This is a deep question here. How does friction work? Like, how normally do you determine the direction of friction? Opposite direction of motion. What does motion mean, though, in this context? Because both of the blocks are moving, M1 and M2. The question is, which direction is the friction force? Yeah, right, M2 relative to M1. But my question here is, what is the motion of M2 relative to M1? So what is the relative motion of M2 to M1? Up and left. Yeah, we have some disagreements. All right, so yeah, so some people have caught on to the point I'm trying to make, which is that because, so M1 and M2 have the same acceleration down the plane. This is because they both have the same, like they both have a force M1G or M2G acting on it. And then these normal forces cancel out the direction perpendicular to the plane. So then the only force remaining on M1 that will cause it to move is M1G sine theta, right? So like the total force on M1 is going to look something like, what? The total force on M1 is going to look something like this, right? M1G sine theta. And then the same thing is true over here. This normal force is enough to cancel out the perpendicular component. And then the force down this way will look like M2G sine theta. And then if you divide by M1 and M2 respectively, yeah. So that means that the acceleration for both blocks is G sine theta downwards. So, okay, to clarify, I think there might be some misunderstanding here. There's no friction here. This plane has no friction on it. There's only friction here. So that means that, yeah, so their accelerations are the same without friction. So there's no need for there to be a static friction force between the two blocks. If anyone has questions, throw them out. There's no motion between M1 and M2. The thing is that there doesn't need to be any static friction because without any static friction, they would be accelerating at the same rate anyway. So the friction force is actually 0. So give me a no if you have a question, or like if something is unclear, Throw it out. Why grid? Because I can draw on this grid. Yes, I said there is static. Oh wait, what is going on? Yeah, there is static friction, but the static friction force is 0. So like if the blocks had relative motion, there would be a static friction force preventing, or like if the blocks wanted to move relatively, then there would be a static friction force preventing them from moving. But because they don't care, they don't want to move relatively to each other. They are moving with each other, like without the friction anyway. So then the friction force is just 0. Okay, I will move on to the next question, assuming that people are okay with that. This is why I said be careful here. The friction force is 0. So part D. Now if this system hits a spring, oh yay, I love springs. A spring of spring constant K is placed on the inclined plane so that block 1 hits the spring and compresses it. Note, so like only block 1, not block 2. Boo. Suppose that block 2 does not slide on block 1. So what I'm saying is that the static friction force is large enough that block 2 will not slide along block 1. So they'll look like this, and then they'll hit the spring, and then they'll go together. So draw and label. So now we're doing another free body diagram. Draw and label all the forces acting on block 1, and then all the forces acting on block 2. Take a look at the diagram to confirm. There's no string. There's a spring. It's a spring. Okay. What's SLHS? Ooh, yes, perfect. Okay. So what is going on now? This is no longer true at all. Sorry, I'm not really reading the chat right now. I feel like someone's probably said something right, but I can't pay attention to all of this. Okay, so let's start with M1. What's going on with M1? What are the forces, the additional ones? Spring, well, the additional forces, yeah. So we already have the normal forces, and then we have gravity. Force exerted by spring, yes. F, the spring. So how do we know there's friction between M1 and M2 this time? Yeah, so there's M1 is getting pushed on. So M2 without friction would keep accelerating at the same rate, but M1 is getting pushed on, so that's not true anymore. We want M1 and M2 to stay together. So like we want the friction force to be strong enough that they have that they can't, it stops them from moving relative to each other. So yeah, sorry, I probably missed it, but which direction, let's start here. Which direction is the friction force on M2? Up. Oh man. We're at 2, 3, 2, 4. Fight. Okay, or not. I guess like we have 4 down right answers and 2 up left answers. You guys better add on what you think to stake your claim. Everyone needs to vote. Down right. Okay. Yeah, there. I feel like there's a pretty. Okay. What just happened? Okay. I'm asking about M2 to clarify. Okay, fine. Suit yourself. Okay, so how do we know the direction of the friction? So So what we want with static friction is for the two blocks to not move relative to each other. Because if they want to move relative to each other, static friction stops them from doing that, right? So that means that the two blocks are being moving together and they're both being pushed by the spring and like decelerated. Well, they're not both being pushed by the spring, but they're both decelerating because they have to move together. So that means the net force on M2 has to be upward. What is that? Wait, what? Okay, so the friction force on M2 is upwards. Friction. Oh, well, so what I'm saying is like anytime while the spring is compressed, it doesn't matter whether M1 is moving or not. But like, let's say right after they hit the spring. What? The force on, so M2 needs to have a net upwards acceleration, or else it will accelerate down. And because they're not sliding against each other, they have to be accelerating up. Or yeah, because the spring is going like boop, and then they're going like doop. Does that make sense? Yeah, they're not sliding relative to each other. They have enough static friction that they're not sliding relative to each other. Okay, so I'll just, their static friction is going up. Can I do split screen? That's a good idea. Wait, hold on. Do I know how to do that? Yeah. I think I could actually do this. Oop. Wait. Go down. Do. Eh. 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 Oh, now I can't see my work. How do I like do the thing? Zoom out a bit. Yeah, here. Why is it on incognito? Because I'm not using my computer. How do I zoom out on this thing? Someone teach me how to use Bamboo. Wait. Alt F4. Yeah, I think I know enough about that to know that I should not do that. What is going on? Why can't I? Okay, I guess I'll just leave as is. Okay, thanks. Anyway, yeah, so this is not the problem we're working on. This is the problem we're working on. And so anyone still have questions about why the friction force is upwards on M2? Okay, I guess not. This is correct. So if the friction force is upwards on M2, then what is the friction force on M1? Yeah. Down right, down right, down, search. Okay, well, we had a couple people pitch in. So I'm gonna go ahead and assume that most of you agree. Southeast. What? Can I explain? So when there's friction between two objects, it's kind of a case of Newton's third law, or that's Newton's third law. Newton's third law again, because yeah, the friction slows down both objects' relative motion. So like, but this is static friction, but it's the same concept as kinetic friction. So like if two objects are moving opposite each other, the friction force is slowing this one down and slowing this one down relatively. For example, this is static friction, but it's the same concept. So they need to be in opposite directions. What is going on? Is the spring attached? No. Okay, I understand this. That's an arrow that goes down into the right. Okay, any more questions about this question? Okay, I will move on. Why is the friction down right? Because Newton's third law. So if the friction is up and to the left for M2, it needs to be down and to the right for M1. You can imagine two blocks like sliding like this against each other, and then the friction has to pull them back, kind of. Yeah. Okay. This is the next question. Assuming that block 2 does not slide on block 1, what is the maximum compression of the spring? You guys can throw out some ideas. What is a thing that you can do? Energy. All right. Okay, enough people have said it. Now I'll go ahead and claim this. So yes, conservation of energy. That is the one technique we have here, because we don't know, like when they're at the bottom, the force is not zero because they're still accelerating upwards. So that doesn't help us. We can't do a force balance. So the only thing left is energy. And well, I didn't actually, what is going on? Go away. So, huh? Okay. How come we can't do a force balance? Because, so imagine like one object is hitting a spring. Then the spring is gonna, like when it's at the bottom, it's not like the acceleration is not zero. So then we don't actually know what the acceleration is at the bottom of the compress. So that means we can't do a force balance. So oh, wait, what am I saying? Hold on. Okay, wait, rewind. What? Yeah, I don't know. Someone called or something. I don't know what happened. So wait, rewind. I'm on the wrong problem here. Oh my gosh. Okay, this is the conservation of energy problem. Okay, so yeah, there we go. That is the conservation of energy problem. The other one, yeah. So I'm sorry. This is right. So on problem E, you do a force balance. So because we're looking for the maximum compression of the spring so that they don't slide, right? And so like, what is the limiting? Like, what is like? Why would they slide if this spring is strong enough? Like, in what would cause them to slide? Yeah. Or yeah. So yes, the force will overcome if the static friction is not big enough, or if the static friction is limited, then it'll become kinetic friction, and then block 2 will slide on block 1. Okay. So we have our beautiful force analyses here. And so what is this? So we're limited by this guy, the static friction. What is the maximum value of the static friction? Oh, I think we should actually go over to this one. This is the one that matters. So yeah, again, yeah. Mu, this is less than or equal to mu F12. Yep. So mu S and mu K are the same in this situation. Yeah. So then, hold on, what am I doing? Wait. Why is this less than mu F12? Oh, well, I just said it was the same. They don't have to be the same. Yeah, it's a given. So as we know, this is less than mu F12. So yeah, so that means this is also less. So, well, first we have to find what F12 is. Can things actually have mu s, mu k IRL? I think so. I'm not sure how common that is, but yeah, I think so. Yeah. So guys, what is F12? How do we find F12? Yeah, it's just normal force, right? So yeah, in order to find the normal force, what you do is you do a force balance. And so yeah, there's this mg, you can break up into these two components. It's the same thing as you've always done, probably. This is m2g cosine theta. So F12 is m2g cosine theta. Mu m2g cosine theta. And then, so the last step here is to force balance on m1. Yes, because what we want is to limit x, and we know all of these numbers already, except for this one and this one. But we just found the maximum value of this one. So that gives us the maximum value of this one. Very good. C. I have one affirmative answer. So this is less than or equal to mu m2g cosine theta. And we know that, well, these two are like, we can just ignore the vertical component of m1g. So the horizontal components of this, we need to balance those. If block two, yeah, this is static friction. So what I'm saying is we're looking for the maximum static friction because we're asking here for the maximum compression of the spring. And so the maximum static friction is this. See, I also wrote this inequality because it's still like, we're looking for the maximum. So let's analyze just the horizontal forces relative to the plane here. So this, we have gravity m1g sine theta. You can stay for as long as you can. Like, no, it should be around an hour, but like feel free to leave in the middle if you need to go somewhere. I mean, I'm not gonna make you stay. Yeah, we're assuming that the height of the block is negligible. Probably. Facts. Okay, so there's three forces here. Well, yes, there is going to be a recording. It's on the website. It will be on the website. F is less than or equal to mu m2g cos theta. And then we have, I shouldn't be drawing separate dots, but they're not, they really like, how do I draw two lines together? So I sent out the website with the invitation. It should be with the invitation. It's just jjophysics.weebly.com. So it's okay if we don't get to like the third problem. I think it's better to like make sure that everyone understands what we're doing. So everyone agree, we want to balance these three forces, right? And we want to find like what is the maximum value of x so that these three forces will balance. This class should be 1 hour. Like, you're free to leave after an hour. I mean, I might stay a little bit longer just to finish up some stuff, but yeah. So we do a force balance. I don't feel like actually doing it, but we can do it. Okay, fine, I'll do it. Yeah, that. I won't do it. It's that. Yeah, it's just this plus this divided by k. So it's a force balance. Next question. Anyone have any comments or concerns? All right. Yeah, so, okay. Next question, from what height must the blocks be released so that block 2 slides on block 1? So I put this after this question, after question E for a reason. Yeah, this is energy, as I've already told you. Yeah, but but how do we know what the compression of the spring is going to be for the blocks to slide? Yes. So yeah, exactly. It's conservation of energy, 1/2 kx squared equals. But then how do we know x? That's my question. Okay, good. You guys have been paying attention. So I will just not solve it, thanks. But, this is the idea. It's important to see. So like, through all of this madness, we have figured out a problem like this. There's a force balance and an energy. Yay. Okay. And now, so anyone have any questions before I move on to the next part? Final part of question 1. Nope. And there's some people in this chat who are much more active than the rest. So last question. This is basically unrelated to the rest. Just putting that out there. So we can't, yeah, okay. For that, like, sorry, I apologize. I meant to say that for F, you can't get it with force balance. For E, yes, you use a force balance. Why did M1 just grow? Well, if you read the question, you will see. Yeah, I mixed up E and F. So E was a force balance because we were looking for the maximum compression of the spring. And then, like, so at that point, they were all, wait, hold on, what am I saying? Yeah, okay, yeah. Yeah, so for E is a force balance, F is a conservation of energy because you can't do a force balance for E, for F. Okay, when net force equals 0, won't there still be a velocity? I'm trying to figure out what's the best. Like, so for E, like the reason, so we're looking for a maximum. So like the optimal situation would be net force is 0, like, and the velocity is, like the velocity is not important. Yeah, so like if, let me think. I might have to like go back and clarify this because like if there's still some acceleration upward, then that means you're still able to compress the spring some more, for example. And like the velocity being non-zero is not necessarily important because the velocity, it doesn't contribute to the force balance. Like, so what I'm trying to say is that like if there was any net upward acceleration left, then you could compress the spring more. And so you can assume that the acceleration is 0. Concerns about that? Where's my mouse? Okay, return to question G. Let me read what people have been saying. Optimal. Okay. So do I want a new page for this? Yes, screw it. Yeah, energy lost to friction is equal to energy potential energy and potential energy lost. So I've seen several of you have been saying for this. Yeah, I agree. This is the main idea of this question. Yeah, that's it. It's literally just the energy lost by friction. M2 slid along M1. So we want to look at the difference between the beginning and the end state of this system. The beginning state is like M1 here, M2 on top here. End state, M2 is a little bit lower. So that means the end state has a little bit less potential energy. And during the sliding, there is some friction. So we've lost all of the energy lost was through the sliding. So that means that the potential energy lost is equal to the energy lost through the sliding. So how do we write this as an equation? We throw it out. Type. Right. So static friction times x equals m2gx cos theta. Okay, so I think I will need a new page. Hold up. No. Okay, new page. Sine. Yeah. Okay, so let us draw this diagram. M1. Ooh. M2. This is its new position. This is x. So so the change, as you guys have said, the change in potential energy is m2g times h, where h is the difference in the heights of these two things, which is equal to x sine theta. And the friction force, the energy lost to friction is the work done by friction, which is F of friction times x. So what is F friction? Remember I told you that the kinetic friction coefficient is also mu. Why is my mouse broken? Why does it keep doing that? Okay, so let's F. Oh, someone just, yep, it's the same as it was on the last page. There is no friction between M1 and the plane. This has been true since the beginning of the problem. Let's see. Yeah, so as the mouse just decided to break on me. That's great. Well, so I guess I'll just do that. Yeah, so it's still the same as it was before, mu m2 cos theta. So this is mu m2 cos theta x. Yep. And so now the question, what is theta? I mean, I think you guys know where to, oh shoot, m2g cosine theta. Yes. Yep. Theta equals arctan mu. This is correct. So any questions about this? All right. Let's move on to question 2. It's tan inverse theta. I can just write this out really quickly just to finish it off. Tan theta equals x. Okay, so question 2. Wow, at last. It's 43 minutes have passed. So